So good morning, everyone. Welcome to the fourth day of the Limit 2024 online camp. Today we have Daibik with us. He's doing his bachelor's in mathematics at ISI Bangalore, and he's currently in his third year. He's primarily interested in combinatorics, graph theory, and probability, and he will be speaking on the friendship paradox. Over to you, Daibik.
Thank you, Rishika. So, hello everyone. I will be presenting my screen. Just confirm if it's visible.
Yeah, it's visible.
Okay. So, if any doubts, you can ask me directly. So, let's start. Okay. So, this is supposed to be an interactive session. So, if I ask some questions or some, please do respond. Otherwise, I won't know that if you're attending or not. So, firstly, let me explain what the friendship paradox is. So, most of the times, you can call it insecurity, but we feel that people like your friends are more popular than you. So it might be that they're not talking to you or something, we're depressed, but uh, whatever be the reason, people, friends, uh, talk to other people, and you feel like you're not talking to yourself. So it is most common that they have other friends, but the question is, are friends more popular than yours? So in fact, mathematically it is true that the friends are more popular than you, or in general, or in average, they have more friends than you. Now, why is this paradoxical? It is paradoxical because even to that friend, say you have a friend A, okay, so for you A is more popular than you, right? But on an average, but then for A's friends, A's friends are also more popular than A on an average. So you are also A's friend, right? Because I assume that friendship is a one-to-one relation. But yeah, so what happens is, to they feel that their friends is more popular, and you feel that your friends are more popular. So both of you are feeling, on an average, the other person is more popular than you. That is why it is paradoxical, and that is the topic on which I will going to talk today. So this is not only true, like in a intuitive sense. This is also true in a mathematical sense. Like, how do we prove it? That is a question. This is a statement. So if I can highlight it. Uh, So the friendship paradox says that on average, an individual's friends have more friends than the individual. Okay, this is the statement. So if you people are following, then please respond if you
Yes, sir.
get what I'm saying. Yeah, okay, nice. So okay, let's take an example. Okay, so obviously we have to consider a friend network, otherwise we can't work. So let this be the friend network. We have these people, and the arrows represent the friendship. So Anila is friends with Devi, Devi is friends with Ashok, and so on. So you can see I have given double pointed arrows, so which means that if Anila is a friend of Nikhil, then Nikhil is also a friend of Anila. This is how it goes. Okay. So, we have to calculate the number of friends of each person and take the average. That is, so average is basically go to 1%, take the number of friends and then divide. So how do you find the average of all the people there? So let's take the number of friends of each people. And I listed that Anila has 5 friends, Devi has 2, Ashok 2, Nikhil 3. So like Anila has 5, means all 5 of them, Devi, Ashok, Ritvik, Nikhil and me. And for Devi, it is just Ashok and Anila. Right. So if we take the sum, it is 18.
Okay, yeah, Daibik. Sorry for interrupting. Are you changing the slides by any chance? Because people are asking in the comments.
Wait, you can't see the slide changes?
No, they were not able to.
Okay, now it's
Yes,
visible.
sir. Now
Now it's
Now
just
we are able to see it.
Wait. So if I go to full screen, so can't you guys see? So like if I go here, Can you see that
No.
I change the
No,
slide?
sir.
No, sir. No, sir.
Wow. Okay, so if I keep it like this, then you can see.
Yes, yes. Now
Yes,
it's visible.
yes.
Rishika, do you know how to present if I go full screen?
I do not have an idea about that. Even last day I was having a problem with the same.
Okay, amazing. Okay, so I will try presenting my screen again. Wait a second, if I can. Yeah, I can create a PDF, but then it won't. Okay, so tell me if you can see the screen now. And if I change it, so can you see it?
Yes,
Yes,
yes.
sir.
Now we can see.
Yes, sir.
Okay,
Yes,
okay,
sir.
okay.
Yes, sir.
Okay, okay. Very sorry, I didn't know that it works that way. Okay. Yeah, I will repeat myself. So, it's okay. The slide will be sent to you so you can read it. This was just an introduction, and let's start with the example. Okay, sorry, I'm so sorry. Yeah, so what I was saying that we take a friend network and let this be our friend network, right? So as I said, the double pointed arrows means that Anila is a friend of Devi and Devi is a friend of Anila, and so on for all of them. And now what we do is we calculate the average, right? So how do we calculate the average? Average means that we take the sum of everybody's friends. Like say Anila has 5 friends, Devi has 2 friends. So we sum all of them and we divide by the total number of people there. And total number of people here is 6, right? So let's see. This is a list. I made a table. So 5 plus 2 plus 2 plus 3 plus 3 plus 3, it is 18. And when we take the average, we basically divide it by 6, the total number of people, which is 6. So 18 by 6 is 3. This is the average number of friends. Okay. Now, if you remember the friendship paradox statement, wait, you didn't see that statement, right? So yeah, this statement. So on average, an individual's friends have to have more friends than the individual. Have more friends than the individual, right? On average. So we found that the individual's average, right? Now we will find the friends average, like the number of friends of a friend. So we have to take the number of friends of all the friends and then we have to divide it by number of friends. So yeah, this was 3 that you guys can remember. Now we first have to list the friends of friends. So how does this work? So let's take Devi for example. Devi can say that I have 2 friends, Anila and Ashok, right? And we take the number of friends of each of them. So Anila has 5 friends and Ashok has 2 friends. You can see from the graph. And so the number of friends of the friends of Devi is 7, right? And we make the table of everyone. So this is Devi that we did earlier. Devi has Anila's 5 friends and Ashok's 5 friends. So we can do 2 things. Firstly, we can take the averages of each friend. Like if we take Anila, Anila has 5 friends, and we take the average. Am I audible? I think the electricity went out for some time.
Yeah, you got it.
Okay, that's nice. So if we take the average, it gives us 2.6, right? In Anila's case. But my statement was that we take the average of all the friends of the friends. That is more than the individual average. When we took the individual average, we took the average of all the friends, right? So we took this was our individual average. Yeah, this is it. So we took all the people and we added all the friends and then we took the average, right? So in the case when we're taking the average of friends, we cannot do it for a single person. And we obviously see when we do it for the single person that it fails. So in case of Anila has 5 friends, right? But her average number of friends is 2.6. That is just contradicting the statement that I gave earlier. And that is why it says that on average, not per person. Though we see that except Anila, all the other people's friends average is more than their number of friends, right? So for Devi has 2 friends, but her friends average has 3.5. And this is how it goes. But it fails in case of Anila. So that cannot be true if it fails in some cases. So what we do is we add all of them. Okay, so we add the number of friends. So like we add Devi 2, Ashok 2, Nikhil 3, and then we add Anila 5, Ashok 2. So we continue this because we consider all the people and all of their friends, and we divide it by total number of friends. That is what the average is, right? So average number of friends is basically total number of friends of all friends by total number of friends. Are you getting my point?
Yes, sir.
Okay, so total number of friends. So we add all these here in the second row, and so what do we get? We get, yeah, this one. So this is for Anila, this part. Okay, if I can show properly. So Anila has 2 plus 2 plus 3 plus 3 plus 3. So this is for Anila. Then the next one is for Devi, I think. Not wrong, yeah. 5 plus 2. Next one for Ashok, 5 plus 2. See, Devi and Ashok are same. Nikhil Ritvik may have same 5 plus 3 plus 3. Right. So 5 plus 2, 5 plus 2, and this 3 for Nikhil, Ritvik, and me. And if we add all of them, it gets 60. And 18, what is 18? 18 is the total number of friends here, right? So it is basically this quantity. So 1, 2, 3, 4, 5. 5 for Anila. And then Anila, Ashok here 2, because we added all these values. So we divide with the number of values we added, right? And the number of values we added are basically 18. You can count here. And when we divide, we get it 3.34. That is greater than 3. This was my statement that the average number of friends is greater than your average number of friends, right? So like the individuals. So this is my statement. Now we showed this with an example, but there are 2-3 points which we need to remember. Firstly, we see that the contribution of Anila, okay, in this average, like in this case, Anila was the one who was contradicting part of my statement, which was she had 5 friends and her friends average was 2.6. It is because she has maximum number of friends, right? But in this case, when I take the average, I see that she is contributing the most part. This 5 into 5 term, which is 25, I think maximum of all the terms, this comes because of Anila's friends, right? So she is contributing the most. Even if you consider here, and that is the part. So we can take a pen. Yeah. So in this case, Anila is a friend of everyone, right? Devi, Ashok, Nikhil, Ritvik, and me. So we take Anila's 5 in Devi, in Ashok, in Nikhil, and goes on. So this 5 term that we see here, it is counted once, twice, thrice, 4, and 5 times. That is why I wrote it 5 into 5. And we see every term, we can group it together. So like, let us consider this one as Nikhil. Okay, so for Nikhil, it is 3. It is counted in case of Anila. It is counted, wait, probably I wrote it wrong. Okay, so Ritvik's friends, this one would be Nikhil. And for me also, this one would be Nikhil. Yeah. Yeah. So Nikhil can be counted once, twice, thrice. right? So if you consider this, so here let me take a different color. Uh, I think this is one. So this is counted once. Okay, these three are for different people, twice and thrice. So if we count it thrice, and that is why I wrote 3 into 3. Now these three hold same for Nikhil, Ritvik, and May, so that is why I wrote 3 here. I just grouped the calculation into number of like the people's friends, and that is what we will do later. So this is what I was saying. So 5 into 5 was for Anila. These three is Nikhil, Ritvik, and May, and these two are for Devi and Ashok. But also one thing to notice, this is 18. What does this 18 stand for? This is total number of friends of everyone, right? So this is what we did here, that we add all of them. This is 18. But again, these are basically the number of friends what we found in the previous case, in this case. Because after all, we went to every friend and we asked number of friends. So when we are adding up, like the denominator here, in the second case was basically the numerator here. This is one thing that you need to notice. So, do you understand? Because the number of friends here would be the number of friends we take in the average in the next case.
Yes, sir.
So, yeah, so this was an example which shows you the paradox, but yeah, this is not a mathematical proof. This is just an example. So I will go on proving it. How do I do it? So, like I told, notice for Anila, she contributes more to the weighted average. Okay, so this is, by the way, the weighted average. The grouping what we did here, this is termed like for every friend we have for like, so we can write this as Anila, is it? So if we consider this term for Anila, so previously what do? We did 5 plus 3 plus 3, right? For every people plus. So now in this case, we are just doing 5 into 5, right? Plus 3 into 3. Plus, you will know about weighted average, right?
Yes, sir.
Yeah. So this is a kind of weighted average. So yeah. And the second thing is I told that the statement holds for the average population and not for every person in general. So we took the case of Anila. Anila had 5 friends, but average of friends I think was 2.6. So this doesn't hold for every friend, like every person, but it holds as an average of all the individuals. So when we take all the averages, it becomes 3 and 3 point, what was it, 3.4 or something, right? So we prove it mathematically. How do we do that? Firstly, what do we need to do is we need to take out the problem in a mathematical sense. We can't take an example and we can go on with that, right? So what is a generalized thing that we can do to represent a friend network? Like, anyone has any idea? How do we represent a friend network in general?
A polygon, maybe.
A polygon, yeah, I mean close, but then firstly it might okay, so a polygon you can consider like this, right? So basically you're saying that you take these two people and like A and B, and A and B are friends with each other, right? And B and C are friends with each other. That is how you consider? Am I getting you right?
Correct.
Yeah, but A and C can be friends with each other, right?
Then we draw the diagonals.
Yeah, so then all the diagonals might not be there. So what is this called? So you connect some diagonals, you might not say connect, it might not be a complete polygon also, right? So like B, this is D and this is E. So A and E are not friends. So how can I take it? Yeah. So wow, Mm. So yeah, it might be like this. A and E are not friends. So then you cannot complete the polygon. It is not a diagonal, in fact. But I think you learned this concept called graphs, right? You had a
Yes.
graph tutorial, I think. Yeah. So in the graph A, B, C, D, E, these are called vertices or nodes, and the lines connecting them are called edges. So what we do is we connect the edge when two people are friends. Like in this case, A and B are friends. So we connect this edge A and A to B, right? So what we start is we take a generalized graph. And okay, so simple undirected graph. I think you know this concept. If you don't, I will explain. It's okay. So let's take a generalized graph. This is the same graph I was working with previously. So this was Anila and all. But yeah, we were not named in this time. We just know these vertices as some variables, say v1, v2, v3, like that. Okay. So yeah, this is a graph. What is a simple undirected graph? Simple means that so there are no, what is it, self loops. So what does a self loop mean? So like this way, v, there is no edge from v to v. Like we know that every person is a friend of themselves, but yeah, we are not considering this in this case. So it will just mess up the average. Hmm. So how do we make? Okay, so like say this is v1, this is v2, and undirected means since everything would be doubly sided. So like if v1 is a friend of v2, then v2 is also a friend of v1. So every edge here we can either give double arrows, like uh, both of them are friends of each other, or we can just remove all the arrows because we don't need an arrow. There is nothing like that. So if there would, I cannot try it again. Yeah, so like say this is v3, this is v4. So there is nothing like v1 is a friend of v4, but v4 is not a friend of v1. So there doesn't exist edges which are directed or pointing to a direction. So all the edges are double directed, or we can just say undirected because they don't, the direction doesn't matter to us, right? And this is the type of graph that we will be using, a simple undirected graph. Is it one? So as I wrote here, the friendships are mutual. Yeah. Friendships are mutual. So, and this is the network. So we don't need to work with this network, but we can use any one network in general. But how do we prove it? We just formulated the problem here. So again, we have to find the average number of friends, right? And we have the graph. So how do we find the average number of friends? So we can call the average mu, start it with a variable. And so for finding average, we will have to go to every vertex and we will see the number of friends, right? So like you can consider this as a friend network and say, okay, what is it? So this is a friend, say V. Okay, this is a person V. So how many friends does this have? This has one friend, two friend, right? Consider this V1. Consider this V2. So this has okay, you don't need the arrows. I'm just trying to 1, 2, 3, 4, 5. Right. So this is what we will be adding, right? So in case we are just adding the number of edges that go out or come in, it doesn't matter, they're undirected. So number of edges from a vertex. So like for this vertex, we just add 2 because there are 2 edges in this vertex. So this term, if you know, if it is called a degree of a vertex. So like degree of V is this one. It is, oh, sorry, it is V1, right? The degree of V1 is 2, and the degree of V2 is 5. So what we are doing is we are summing up the degrees of all the vertices here, and then we are dividing it, like as we are taking an average, we are dividing it with total number of vertices in the graph. That is what we are doing for an average. So we can write mu is basically equal to summation of the degrees of all the vertices. I took V in V, capital V is the set of all vertices in the graph. And we take this summation from V, we take V for every V, and we divide it by the total number of vertices. You get it?
Yes, sir.
So this is the first thing, the average number of friends. The harder thing is to find the average number of friends of friends. But we will go to that a bit later. We will first modify this a bit. So yeah, okay. Yeah, remember this term here, the summation of dv, like we go to every v and we take the degrees and we take the summation. Okay? So we can write this, what I'm claiming is we can write this is 2 into the number of edges. So what I'm saying is, in this case, that you take the summation of all these and it is basically 2 into number of edges. So in this case, we know that this is 18, right? This summation of dv, because we know this graph. This was the same graph that we were using previously. Okay, so let me show this. Remember this thing? See, this also has a point on top and the 5 points distributed like this. And here the same graph, yeah, like this, 1 point on top and 5 points distributed like this. So we know that this is 18, right? Let's take the number of. So what is the number of edges? What do we count it? We take E4, E5, E6, E7, E8, and E9. So we can say there are 9 edges. And if you remember here, I said that summation of dv equal to 2 into number of edges. So it is just summation dv for all v from v equal to 2 into 9, which is 18. And now we know that this result is correct because we checked it previously. The number of friends are 18. So this claim holds true for that graph. How do we prove it in general? Like for every graph, this holds. Now, for proving this, I will use a bit of combinatorial argument, or what we call it. So take here, when we take a vertex A, okay, so I took another graph, so I'm basically working with general graphs. So I take a vertex A and we find the degrees. So we consider this edge once, this edge once, and this edge once, right, for A degree. And then we find, say, D's degree. In case of D's degree, we consider this edge once and this edge once. Now, when we take, say, C's degree, I'm running out of colors. Okay, so C's degree, we consider this once, and this once. And say when we take B's degree, we consider this once and this once. So now if you see, every edge has 2 colors on it, right? This is true because every edge is surrounded by 2 vertices. So when we consider, say, this is some V and this is some W. Wait, I think this color is not that visible here. So when we take the degree of V, this edge name is VW. This edge is counted once, right? In taking degree of V, and when we take degree of W, this edge VW is counted once again, right? So and again, so in the whole graph, this edge will be counted only twice, because once when we take degree of V and once when we take degree of W. Any other, as there are no vertices here, so we take some, say, random vertices, say A, disconnected with V and W, but this edge VW won't be counted here, right? So when we take the summation of all the vertices, like the degree of all the vertices V, every edge will be counted twice because it has two vertices. There exists no edge like there is a vertex here and the edge continues here with no vertices. That is not possible. So every edge surrounds two vertices and it will be counted twice. That is why when we take the summation of all the vertices, we have to take twice number of all the edges in the graph. Get the intuitive feeling? How this works? I wrote it properly. So yeah, you can proceed. If I can, I will. Yeah. So it's written here. So like every edge can be taken in consideration twice, and hence the summation is basically 2 into E. Right? So remember this thing. Here we had mu equal to summation of dV by V. We can write this easily as, say, 2E by V, because this and this are equal, right? So we got our one quantity, which is mu equal to 2E by V. Now let's work on finding the average number of friends, which is a bit harder than this. We denote that by mu f. So what do? We take a general graph and we take the average number of friends. So what we'll do here is we go to every vertex. Okay, so let's name the vertices again. V1, V2, let's say V3, V4, V5, and V6. So what we do is we go to each vertex, say V1, we take all the neighboring vertices of it, which is V2 and V3, and we add their degrees because we have to take the number of friends of friends. So we take V3's friends and we take V2's friends. So we take a degree of V2, degree of V3, and we add. And this quantity is being added only for V1, right? So for V3, I will add a degree of, say, what does V1 and V2. So basically we travel to every vertex, we take the neighboring vertices, and then we add the degree of them. That is what we're doing. So if you allow me, so this is basically take a summation over all V's in the graph. Then we go to their neighborhoods, and neighborhoods means, so like V is neighbor n of V1 is basically the set of V2 and V3. Right. So we travel to this V's neighborhoods. So like we take NV, and so we travel through every every U in NV. I am using a different variable, and we take the degrees of U. This is a double summation. So like for every vertex, we travel for all the neighboring vertices and we take the degree of all the neighboring vertices. That is what we are doing. So okay, I will have to rub this. Yeah. Yes. I can keep one example. But this everything else is written. Yeah. Yeah, so the double summation of the degrees of the neighboring vertices of every vertex. So we take it as summation of v in v du. Okay, where u are the vertices in NV. Now, okay, while we divide it, like the average we are taking as all the friends. So we will consider for V1 we are taking V2 and V3. And for V2 we are taking V3 and V1 and V4, V5, V6, all of them. V3 I'm taking V1 and V2. So this is basically the same thing that I told to notice earlier, which is the denominator in this case is basically the numerator in the mu case. And we know the numerator in the mu case was the summation of all the degrees of all the vertices. So that is the denominator here, which is summation of V belongs to V dV. You notice it here. This was, yeah, this was the numerator in the previous mu case, summation of V dV. Yeah. So obviously we will have to make it in a format which is, say, like comparable to mu. Right now this just looks a bit weird because we have two summations in the top, one summation in the bottom. Okay, so this summation can be represented easily. Okay, we know that this thing corresponds to two number of edges, right? This is what we proved in the previous slide, but we need to simplify this thing also a bit because this just looks complicated. So we'll try simplifying that. We claim that as a summation of dv square. So like this is the summation of every vertex and we take the degree of the square of the degree of that vertex. So again, this looks, we need a combinatorial argument to prove this, which is why we take a general graph and let's see what is happening here. So let us consider. Previously, we while proving that the summation of say v belongs to v dv equal to 2e, what we did is we saw that every edge was being taken twice, right? Now we consider one thing here. So let's take a. Okay, what we are doing is we are going to every neighborhood of a. So like we are considering, okay, let's take it. I'm writing it here. So like neighborhood of a is D, C, and B, right? And what we are doing, we are going to D, and we are taking the, what do you say, the degree of D, right? So degree of D is taken in consideration for A ones. But similarly, when we are taking consideration C, so like C belongs to V, right? So we go to neighborhood of C and we have D and V here. Wait, we also have A, sorry. DBA. So even while considering C, we add the degree of D, right? And I think that is the only two times while we are adding the degree of D in this whole summation. Okay, ask me if you understand or if you do not understand, so I will answer. Feel free to stop me. So this is only two times while we're considering the degree of D. Now for the degree of A, we will consider it once we consider D because A lies in neighborhood of D. We will consider it when we consider C because A lies in neighborhood of C, and we will consider it when we consider B. A lies in neighborhood of B. So for general vertex V, we will consider degree of V for all the neighborhoods of V, right? But how many neighborhoods are there in V? So basically, we can say that the number of points in a neighborhood of V is basically degree of V. So a degree of V is being considered these many times. So you can just write that we are considering any degree, its square mean. Like we are considering the degree square in the summation. So like if we are adding this many times, so we are basically adding the square of that. Right. So in the whole summation, it is nothing but we go to every vertex and we take the square of the degree and add it. Do you understand?
Yes, sir. Understood.
Yeah, so I wrote everything there. And we can just show it that very sure. That yeah. So the summation of double summation over v and nv of du, we can write it as a summation of dv square. So what did we get here in the previous case? We got this. The denominator was obviously 2e, but we got the numerator as summation of v belongs to v dv square. This looks quite simplified. So we write it. This was mu. Mu is 2e by v. And this is mu f, which is summation of dv square by 2e. But still we can't compare these quantities, right? So if it, because say like we don't know the number of vertices or the number of edges in a general graph, we are working with a random friend network. So we cannot say that. So what we have to do is we have to manipulate it a bit further to reach a comparative value. Right. So how do I, that is my question is, I have this quadratic term here. All the terms here are E, V, E. So like, how do I make the quadratic term disappear so that this quantity is comparable with mu, as a mu? And there we used a statistical quantity called variance, if you remember. So variance is basically we take the square of all the values from the mu and we divide it. That is where there's a chance of appearance of dv square, right? If we have the variance, which is denoted as sigma square, then we can compare it to mu, because we can write sigma square in terms of mu, right? So, but how do we calculate the variance? So we have to first calculate the variance and then we have to compare it with the term mu f, so that we can put a sign in between them. So like say less than or greater than or some equal to, something like that. So yeah, I have to find the variance. How do we find it? Now, you know the variance is a measure of dispersion, right? So basically what we do is we take the average value mu, we take all the quantities dv. So I'm taking the variance of number of friends. So I take all the quantities dv and we subtract it from the average, take the square, take the summation of the square, and we divide the whole thing by total number of things that we're taking summation on. So here we were taking summation for all the vertices, we divide it with the number of vertices. Right. So this is the term here. This is our standard variance term. Now it's just calculation. So we see a square formula here. So this is basically a plus b, actually a minus b whole square. We just expand this. This is a square minus 2ab plus b square. Okay, so now what we do is we break the terms. Right. So because the summation is in brackets, so we have to break every term in the summation. So it is summation of dv square, the first term, divided by like mod v, or the number of terms, number of vertices. Then we take summation of, okay, so minus summation of 2 dv mu. Now remember the summation is over v. So this term, the mu, it is independent of the summation. we can just take this out. Also, the 2 is a constant, so we can also take this out. So we can take out 2 mu of the summation, and the summation is of dv by v. Okay? Similarly, for the last term, mu square, it is fully independent of the summation because summation is again v. So we just take out the whole mu square, and it is basically summation of 1 by v. Okay? No confusions till that point, right? Hello. Am I audible? Okay, nice. So, yeah. So now we will, now we can just reduce these terms. So the first term, we cannot do anything because we need this term. So if you remember, we are doing all these just because we need this term, dv square, right? So we won't touch this term. This term is added as we are leaving this as it is. And what about the other terms? So this term looks familiar, right? This is basically what we found here. If you remember, wait, can I just go like here? So remember this term, mu was basically summation of dv by v in its the first format that we found this, and even here we have it as we have it as summation of dv by v. So this term is nothing but mu, the whole box term, and this term. Okay, so what is the numerator? Numerator is summation of v belongs to 1 to 1. Okay, so let's understand this term. This term is basically we are adding 1 for every v in v, right? So we are basically getting the total number of vertices here, because for every vertices we are adding 1. So the total number of vertices, this is nothing but the total number of vertices. So if this is v and we have v in the denominator, so then we can just cancel this. And this term becomes 1. So we have the first term as it is. Second term is 2 mu into mu. And the third term is mu square into v by v. So this is 1. So we have minus 2 mu square plus mu square, which is this whole term minus mu square. Because minus 2 mu square plus mu square. Now we just bring this mu square, this one to the LHS, and we take this one to the numerator on this side. So this manipulation is sigma square plus mu square equal to this. We take this v this side. So this term, what we required earlier, for which we did all the calculation, this was used in mu f, if you remember. So we formulate this term as sigma square plus mu square into v. And as we said earlier, so from the variance term, we are getting a mu term. And now we can compare these quantities. So what we do is we just substitute this value in mu f. And how do we do it? Mu f was this. Now we found this value is equal to this, so we substitute. This is sigma square plus mu square into v by e. Now notice this term again. This is basically v by 2e. I can write this as 1 by 2e by v. Right. And 2e by v is nothing but mu. Right. If you remember, we found it here before all the manipulation. Yeah. Mu was basically 2e by v. So what we do is we put all the values here, and 2e by v is basically 1 by mu. So we can write it by mu. And now it is we just break the term, so it is sigma square by mu plus mu square by mu, which is mu, right? So now if we compare them, wait, I wrote it on this one. How do you find it? Yeah, so if you compare them, I will get these terms. So mu f is basically mu plus sigma square by mu. So I wrote it that this is greater than mu, but for that we need this term to be positive. Right, if this term is positive, then we're adding mu with some positive value. It is obviously greater than mu. Now, why is this term positive? Because we have a squared term in the numerator that is obviously positive. And for mu, mu is basically the number of friends, basically number of friends of friends by the number of friends, number of people. So now this is positive because, okay, so what is the least thing that you can have? So it is, say everybody has 0 number of friends, right? Which is very improbable, but it might be the case. So we have just a collection of dots or vertices, but no edges, because nobody is anyone's friend. So the numerator, the least value of the numerator can be 0, and the denominator can just be will be, which is 0, right? This is the extreme case. But if anyone has a friend, like if we connect any of these vertices, this number will just increase to 2, because again, one from friend and the second friend returns a symmetry. So this is, in fact, we say greater than equal to 0, because the least value is 0, but connecting any of the edges make it more than 0, so it is greater than equal to 0. That is why we have to write that mu plus this thing, or just mu f, is greater than equal to mu. This equal to value if there's a totally isolated graph, like all the points are just points and no edges, right? And this was our proof, because we need to prove that this case holds, and that actually holds. The averages, like of the friend's friend, is more than the individual friend's average, and we proved it. So this was a bit of this manipulative calculation. If you guys understood it, it's nice. So now we will go on understanding what it is actually. Okay. Rishita, can I continue like 10 minutes more?
Yeah, sure, you can go on. The next term is at 12, so you can go for 15-20 minutes if you want.
Okay. Thank you. So yeah. So we have to understand the mathematics behind it, right? So basically the manipulative calculation doesn't make sense if we don't understand the intuition or the concept of what we are being told here. So yeah, now I've used a term here which is sampling bias. So this is what the whole friendship paradox is. It is a sampling bias because it is a statistical error. We are making the mistake inherently without even considering it. So like, how is it happening? So like we proved it earlier that it always happens. Then obviously this is a paradox, right? So this is not supposed to happen, but it happens. So we are making a mistake somewhere. And what is a mistake? What are we not considering while taking the calculation? Okay, I gave it an example, I think, yeah. So this is not just related to what I did, but this provides an insight. So like this is a Harvard, it is taken from the site of Harvard College, and it has a line here that says the median class size at Harvard is 12. Okay, so now this line is a bit like, let's say, dubious. So this makes you understand that the class sizes in Harvard are basically low, right? As the median is 12, so there might be some classes which are less than this, so there might be some classes which are more than this. But since it's a median, it is the value, say like, you know what a median is, right? So if you have some values, say a1 to an, and we take the middlemost, we arrange it in some order, so let's say ascending or descending, and we take the middlemost value. That is what median says. So now it is said the median class size is 12. So there might be some values which is less than this. There are some values which are more than this. But it is 12 in the middle. So obviously, even if it goes more, how much more can it go? It might go to 20, it might go to 30, 40. It's okay. So we don't get a general idea of what a class size in Harvard is, right? We basically think it is very low. And there might be some classes with high class sizes such as 40, or you can say 50, but there are less classes of that. More the classes are obviously in the middle, so which lies say from 8 to 20, 25. I think this should be the range that comes to a normal human mind, right? So if you go to Harvard, you're supposed to be set up in a class which has less population, so obviously more student teacher ratio, so it will be good. But this is not true. That is how the statistic fools us. Let us say how it is misleading. So we can take an example, say classes A1 to A5. So 8, I wrote 6 classes, actually 5 classes. Yeah, so the 5 classes A1 to A5. And say class sizes are 1 for each first 4 and 96 for the last one. What does it give us? It gives the average class size as 20. Now this is the mean class size. But this doesn't give us an idea of the true representation, as we see that the 96% of people, which is in class A5, there are 96 people. So the 96% of people are in a class size of 96, but we're still getting the average as 20. This is because the people like who are in less, so from the classrooms A1, A2, A3, they are pulling the average down. We cannot say for sure from an average, as there might be values or pull downs which can just manipulate the value in such a way to make it look as a proper value, when in fact that is not how the representation works. So in every case, we take the weighted average. When we take the weighted average, we have it as 1 contributes 4 times, so like 1 into 1, 4 times, and then we take 96 into 96, because every student in the class would say my class average is 96, and then we sum it over all the students, because we go to every student and we ask him or her, what is your class size, and they will answer with them. So 96 people will answer with 96, and since we went to every student, we will divide it by 100, and this gives us the weighted mean, which is 92.2. This is a representation. This is also not the correct representation or the most accurate one, but this gives us a better idea than the 20 here, which is just misleading, right? So again, if we go to the previous example of the Harvard class, so if we actually make the deviation and the correction to the median, the average class size is 73.4, right? And that is how misleading it is. So it was given the median class size was 12 and we're getting the average class size is 73.4. It just says that we just can't trust statistics, right? Because if we don't know it properly or if we don't calculate it properly. But then you might ask that in the friendship paradox, we are considering the weighted average. So what is the problem there? Because we just saw that the weighted thing gives us a more accurate value. Now, there is one more thing which we don't consider. That was called sampling, and now we consider the bias thing. What is the bias? Had in this case, we are not considering all the people. So say there are 1,000 people. So it is not possible for us to ask all the 1,000 ones, right? So what we do is we ask, say, 5 100 people in random. Okay. Now let us extend this case. So, okay, can I use something else? Say I'm using white screen. So let us take the cases from A1 to say A1000, where every class till A999 contains one student, and this class contains say how many? It is 999. So say content like some a big number of students. So let us just name the number C. Okay, C is very large. Now we are asking on an average, so by random, right? We are asking random students because we cannot take all the students. We are asking random 500 students. What is your class size? To say, what if the random students are selected all from the first 999 classes? So everyone will answer their class size is 1, and we will take 1 into 1 for 500 cases, and we will divide it by 500. So our what to say, the randomly sampled randomly sampled weighted average also gives us 1, right? But it should not be the case if you are taking 500 students from 1001. So why are all the students from the classes which are 1 student? It should be equally distributed, right? From the like from all the students. So we have to take some students from 8000, we will take some students from these classes, and we will get a more or less optimal value, or a value which is close to the actual average. But here we are getting 1, which is not the true representation. So we say that the randomly sampled, which with the random sample that we took to measure this average, is biased. It is biased towards the low class size group. This is a common phenomenon. So this happens quite a few times. So like I'm giving an example. So like say you're good in some sports, say football. Okay, and what do? You start playing football, you start playing good football, you start being selected in some, say, district level or state level, and you start comparing yourself with the players of the state level. Say you're going through an underperforming patch, so you start comparing yourself, so like with the players who play good, like in your level, the state level, right? And you start saying that okay, I'm not playing as according to their standards and everything. But to see it properly, your data is biased, as in you're comparing yourself with the players who are actually good in the sport. You're not comparing yourself with the players who say are learning it. You are quite better than that, but you are still not comparing yourself, and you're comparing yourself with the people who play at a higher level than you, and you are basically depressing yourself. This happens in every field. This also happens in educational fields, like you're comparing yourself to a toppers and you're getting depressed that you're not performing well. But in fact, you are performing well as compared to all the population of all the classes, say, in India. That is taking a biased data set. Even in this case, the friendship population is biased because, say, you are friends with only the people who are popular or extroverted or have some likable quality. You're not friends with the guy who just like sits quietly in a corner and everything, because he would have less friends in general. But when you take the people whom you are friends with, they will like are more popular. So you are comparing yourself with the more popular kind, and so they will in general tend to have more friends. I'm not saying again just for you as an individual, this is for the average people. So if we take a set and we take the averages of both the side, we will see that the friends of the people are more popular because they are in general having more friends. You get it? My statement is a bit cyclic. That is why it's a paradox.
Yes.
So this is my explanation of the paradox, and you can ask any questions if you have. Otherwise, I will just complete an application. So yeah, do you guys have any questions?
Sir, can you give some more examples on sampling bias?
Sampling bias. Yeah. Okay. So uh, yeah. So what is the name?
Ananya.
Yeah. So like, do you do so like say, are you going to the gym or something like say for bodybuilding or some purposes like that?
No, sir.
Okay. So say there is something passion. Okay, what is your hobby? Like, if you do something or like that, like the
Sir,
drawing or
programming.
singing. What?
Programming.
Okay, so programming. So you probably practice it in some websites like Leet Code or something. You solve problems, right?
Yes.
Yeah. So what is your rating?
Currently like 1000 something. I am not
Okay.
good right now.
Yeah. See, this is the problem. So you're saying that you are not good rated. Like it is 1000, and if you see the graph of all the people practicing in lead code or something, so you see that okay, what is the base rating from when it starts? Like, what is the first rating that you get?
I don't remember now, but
Okay, let us just take it as 500. So this starts from 500 and say you are in the 1000 range, and so it goes on. I think there are grandmasters of 2500 or something. So if you take the lead code graph, it goes like this. So say it has something, mostly this follows a normal distribution. Okay, this we will learn later, but yeah. So what you are is, you are kind of here, right? So I think most of the people, the peak forms a bit later or a bit earlier, I don't know, but most of the people are here, right? So you are at par with the most number of people in your rating, and there are more rating, like the more people who are behind you, and there are some people who are ahead of you, but the number is less. If you see this graph carefully, then it is not an actual accurate graph, okay, but this represents that the people who are behind you are equal to the number of people in front of you. Like, there is not much difference to the people who are ahead of you and the people who are behind you, right? Because obviously there are less people with higher ratings, and you are comparing yourself to the people with higher ratings, and you're saying that okay, I'm not good or something, but it's not. You are also greater than like about half of the population. Not half, sorry, but say about 35%, and say about 35% is higher than this. So you have to take out the percentile where you lie, and then you have to compare it. Again, the percentile may lie, so you have to take the weighted percentile, or you have to take some correction terms to take the actual region where you lie, right? And
okay, sir.
actually, I think if you take the percentile or something, you will get it. So my point is that you say that you are bad only because you compare yourself to the people who are ahead of you and not the people who are behind you. If you take a random sample, you might say that you like very close to the median, like either this side or this side. If this is a median, the median represents the middle value, so you might lie here or here, which is not very bad. So that is my point. When you're taking a bias sample, you're taking the people who are ahead of you and not the generalized one. A truly general random people would leave you in the middle.
Okay, sir.
Did you understand
And
better?
yes, sir. And so I have also one question that Recently, there was a school project, and we had to conduct a survey on the health of the people in nearby residents. So, if we want to identify our sampling bias in that particular survey, then how can we do that?
Okay, sampling. Okay, health situations. Okay, I will consider an example, an application after this. So that will probably answer your question. Or
Okay.
and yeah, and also if you see, so okay, it was a survey on basis of like some specific disease or just in general.
No, sir. It was majorly on we were trying to identify the impact of underground water on the health of people of that particular area.
Hmm.
So we had
So,
means a waterborne disease, all of these type of things in
so
the
yeah,
survey.
so what you have to do is you have to basically vary all the factors which are necessary in this case equally. So like you have to vary all the age groups, you have to vary all the regions, you have to vary all the available conditions. So like the clear drinking water or the living conditions. So try varying all these qualities evenly so that you get random data sets. So like you take one to the extreme, one to the middle, one to the extreme. So if you take, like, say if you say there is a factor x, okay, and you take all the your people that you're consideration, so on one extreme of x, so we say that your data set is biased in terms of x. Right. So don't let that happen. You just distribute them evenly over every possible condition X or whatever there is. So like take people from every age group, take people from every residency, and then try to find the correlation or something, whatever it's told. That is how
Okay,
you avoid bias.
okay, sir.
Anyone else? Okay. So if there's no one else, I will just tell an application. So we learned what the paradox is, right? So you might ask, why is this useful in our lives? So as you saw here, this just represses us that if my friends are more popular than me, let's consider an example. So as he was saying, so medical survey. So like in say a decade earlier, I think, yeah, there was no, I don't remember the date. Yeah, so there was a flu outbreak. Just take a hypothetical situation. There is a flu outbreak, and we have the notice, okay, that there would be a flu outbreak, and the scientists are given time to study it. So what do? They track a group of people who are prone to, say, the condition. So like the flu can happen morely in just an hypothetical situation in corporate offices. So we take people from every major corporate office and we inspect them. We basically keep a health track of them so that if one of them is say infected with the flu virus, then we will get to know it early because they're more prone. So before it spreads to the general population, we will get to know it and we can just work on the treatment, right? So what the scientists did, they took two groups of people. So they took a group of people from every major corporate office, and the second group is they told every one of them to pick a friend of yours. So every person in group one picked a friend, right? And that constituted group two. The scientist took both of them separately and studied them. Now, the amazing result is that the second group of people, they were, were obviously more likely to catch the flu because, again, the bias, because they are more popular. So they have more people in common with, see, the first group had all of them as their friend. So they will obviously receive it from them. And they also have other friends and they can also transmit that. So they can receive it from the other friends, they can transmit it to these group one people, or they can receive it from group one, or they can transmit it to other people. So in both the cases, they are the ones who have more chances of catching the flu. And that is it. That is what happened. So This group, we call them the super spreaders. They caught the flu about 2 weeks, again on average, earlier than the first group. So as we see, we took a group in random, but we use this bias to our advantage. This is an example where it can be useful. So yeah, references, and I will send you the slides. You can study from there.